Good morning, everybody. Hope you're all healthy and safe. We shall continue with our lecture on chapter 6 about self-adjoint operators. So in the first lecture we had discussed what is meant by self-adjoint operator, and we had seen a few properties of self-adjoint operator. In this lecture we shall continue with discussing the more properties of self-adjoint operators. So property 6.1.5, that is, let C is equal to supremum of modulus inner product AXX divided by norm x square. Okay, the value of C is defined to be as follows. Then if A is a symmetric operator, we have C is equal to norm of A. Okay, that is the property. If A is symmetric, then C and norm of A will both be equivalent. So let's see how we can go to the proof of this. For this, first of all, let us consider modulus inner product AXX. Okay, now by Cauchy-Schwarz inequality, we have this is less than equal to norm of AX into norm x by Cauchy-Schwarz inequality, right? Okay, so and norm of AX can be further can be less than or equal to by the property it is equal to norm of A into norm of X and into norm of X, so that is norm of X square, right? So this implies modulus of inner product AXX by norm x square will be less than equal to norm A. Okay, this is for every x not equal to 0. So if this is true for every x, then I can say that supremum over x not equal to 0 modulus inner product AXX by norm x square will also be less than equal to norm of A. The supremum value will also be less than equal to norm of A. That is, C is less than or equal to norm of A. So one inequality I have obtained. Now for the reverse part, to obtain the reverse part or reverse inequality, consider inner product of A of x plus y minus inner product of A of x minus y. Okay, after simplifying this, I can write this as A of x plus A of y x plus y minus inner product A of x minus A of y comma x minus y. Now by the property of inner product, I am just going to expand this. That is A of x comma x plus inner product A of x comma y plus inner product A of y comma x plus inner product A of y comma y, and there is a minus sign, so minus inner product A of x comma x and A of x and minus y. So that will be minus of minus, that is inner product AXY. Then we have minus and minus again plus, that is plus inner product AYX. Then we have minus plus and a minus, so that is minus inner product AYY, right? So the terms will get cancelled, right? And I get this is equal to 2 times of inner product AXY plus AYX. Okay, right? So this can be simplified into this form. Now let's see why did we do that. So 2 times inner product AXY plus inner product AYX was equal to inner product A of X plus Y. I'm just writing it again, okay, minus inner product A of X minus Y, X minus Y. Now if I take the modulus, 2 times modulus inner product AXY, plus inner product AYX, this will be equal to modulus of this whole term, right? And by triangular inequality, this will be modulus A. I'm taking this as one term and this is another term, so modulus of A minus B would be less than or equal to mod A plus mod B. So I can write this is less than equal to modulus of A, right, plus modulus of B, X minus Y, X minus Y. That is by triangular inequality. Okay, when I take the modulus value. So that step is clear, I hope. So now this term can be written as, this is less than or equal to C into norm of X plus Y whole square. What was C? C was nothing but supremum of modulus inner product AX X by norm X square, right? So here also we have A of X plus Y, X plus Y. So C into, C is the supremum value, the highest value. So any term modulus A of X by norm X square will be less than equal to C. So that term is less than equal to C, and the term norm X plus Y square will be coming as a product of this, right? So this is less than equal to C into norm of X plus Y square, and this is less than or equal to C into norm of X minus Y whole square by the definition of C. So I can take C common, so this is C into norm of X plus Y square plus norm of X minus Y square. Okay, so let's see what we have got. I have obtained 2 into modulus inner product AXY plus inner product AYX is less than or equal to C into norm X plus Y whole square plus norm X minus Y whole square. This is what I have obtained finally. So this implies modulus inner product AXY plus inner product AYX will be less than equal to C by 2, taking this 2 on this side, into norm of X plus Y whole square plus norm X minus Y whole square. Now recall what was parallelogram law. Here we'll be using parallelogram law. Okay, by parallelogram law, this can be written as C into norm X square plus norm Y square. Okay, parallelogram law is norm of X plus Y whole square plus norm of X minus Y whole square is equal to 2 times norm X square plus norm Y square. So I am replacing this by norm X square plus norm Y square. So this is the inequality that we have obtained. That is, keep this inequality in mind. Inner product AXY plus inner product AYX, right, is less than or equal to C into norm X square plus norm Y square. Okay, now we'll move to the proof. For the proof, what I'm going to do is, let X be any vector with norm X equal to 1 Okay, and let y is equal to ax by norm of ax. Okay, and we are considering the case when x is not equal to 0. Okay, otherwise a of x is not necessary to be defined. So y is ax by norm of ax. Now if y is ax by norm of ax, what will be norm of y? Norm of y will be 1. Now I'm going to substitute this in the last inequality that we have obtained. So we get modulus inner product ax y. Y is ax by norm ax plus inner product ay. What was y? Y was ax by norm ax comma x is less than or equal to c into norm x is 1, norm y is also 1, so c into 1 plus 1, right? I'm just substituting the value here. X is as it is and y is replaced by ax by norm ax. Now this is a scalar product, right? So I can write this as inner product ax whole divided by norm of ax, and plus we have that the operator a is symmetric, so this is same as inner product ax by norm ax comma ax, right? Since a is symmetric, right? So this can be again written as inner product ax by norm of ax. This is less than or equal to 2 into c, right? What is inner product ax? That is nothing but, or I'm going to write it first like this as 2 times of inner product ax by norm of ax is less than or equal to 2 into c. Now inner product ax is nothing but norm ax square, so norm of ax square by norm ax, that is 2 times, is less than or equal to 2 times c. So this implies 1 ax gets cancelled, 2 and 2 gets cancelled. I get norm of ax is less than or equal to c, and this is for every x not equal to 0. So for supremum x not equal to 0, norm of ax will also be less than or equal to c. Now this is nothing but norm of a, so norm of a will be less than or equal to c. So I have got both the inequalities. First we have proved that c is less than or equal to norm a, and now we have seen that norm of a is less than or equal to c. Therefore we can conclude that c is equal to norm a. Now just remember, we can get this inequality only if the corresponding operator is symmetric. We have used that, and that is only possible when the operator that we are considering is symmetric. So this was the property. This was a simple proof. We just have to remember the step that we have used properly. So just go through the property again and the proof of it. So that's it for today's session. Thank you.